Hi students, welcome to lecture 9, which is entitled Small Bodies in the Solar System. In previous lectures, we've talked about the solar system as a whole. We've talked about the 8 planets, and we had actually a separate lecture for Earth and the Moon, and then a separate lecture for Mars, and then the other 6 planets were discussed in a lecture entitled The 8 Planets. In this video, I want to finish up our discussion of the solar system by talking about small bodies in the solar system. In addition, I should just mention that we've talked about the Sun, which is at the center of the solar system, and that contains the vast majority of the mass of the solar system. And the rest of the solar system contains or consists of planets, dwarf planets, and then other small solar system bodies. I covered the constituents of the solar system in a lecture. I'm sorry to say I can't quite remember which lecture off the top of my head here, but the first slide in one of the lecture videos lists the constituents of the solar system officially and their definitions. One of the aspects of this lecture, which is a little bit tricky, is to understand the difference between a dwarf planet and a regular planet. This was actually covered in the lecture that I was just referencing, but before I continue, I just want to make it clear what a dwarf planet really is. A planet is an object that orbits the Sun and has enough gravity to be spherical and has cleared its orbit of debris. A dwarf planet is an object that orbits the Sun, has enough gravity to be roughly spherical, but hasn't necessarily cleared its orbit of debris. I'm paraphrasing the official definition, but that's the basic idea. There are likely many dozens or hundreds of dwarf planets. There are 5 recognized ones, which I have here. The reason there's only 5 recognized ones is because dwarf planets aren't easy to find, since, as the name implies, dwarf planets tend to be quite small. Dwarf planets are basically large asteroids. They haven't cleared their orbits of debris, which means that their orbits really look like those of asteroids, except that they're not, they don't look like, I should say, chunks of rock. Obviously, they are chunks of rock and ice, as are planets, but they look sort of like mini planets, which is why we call them dwarf planets. I will get to the orbit part a little bit later when I show you pictures of the solar system. Let's talk about where asteroids are in the solar system. The answer is basically everywhere, but there are particular regions that are repositories for asteroids, meaning that there's a lot of them there. And when asteroids, for example, hit Earth, or come toward the inner part of the solar system where Earth is, they often come from certain regions. One of those is the asteroid belt. This is a region with millions of asteroids, and it is by definition from 2 astronomical units from the Sun out to 3.3. There are certain objects, such as asteroids and comets. We will get to what comets are in just a bit, and what asteroids are in a little bit. But there are certain objects, bits of rock and ice, basically, that regularly approach Earth, and these are referred to as near-Earth objects. There are people who catalog NEOs, near-Earth objects, and in addition to objects in the solar system just being inherently interesting because they're unknown, we care about near-Earth objects because they may pose a threat to Earth. And I do want to mention that the dinosaurs, as you probably know, are thought to have died out largely from, or maybe entirely from, an asteroid which hit Earth about 65 million years ago. Dinosaurs had an extremely poor grasp of the solar system and other astronomical phenomena, and hopefully our understanding of the solar system is a little bit better and we can protect ourselves from asteroids. I will talk about that a little bit later in this lecture. Let's talk about what asteroids and comets are. An asteroid is a hunk of rock, basically, that orbits the Sun. It's not large enough to be a planet, and therefore we call it, an asteroid. I mentioned before that dwarf planets are basically large asteroids. There are generally three types of asteroids that are defined based on their composition. We have C-type asteroids, which are largely carbon-based. We have asteroids that are composed of silicate with metals. Those are the S-type asteroids. And then we have the metallic M-type asteroids. A comet is an icy body that passes close to the sun. And therefore, a comet is a rocky, icy body that produces a tail as it passes close to the sun, because if you bring ice close to the sun, it will sublimate. It will turn into a gas. I will get to that a little bit later. I think that most people have a picture of what a comet is. It's an object that travels, from the perspective of an earthbound observer, it travels across the sky and then has a tail. And the tail is produced by the heating of the ice from the sun. Let's look at a picture of the asteroid belt. This is not a real picture. This is just a diagram. But you can see here we have the sun in the center. Then we have the 4 terrestrial planets, Mercury, Venus, Earth, and Mars, in order. And then we have the asteroid belt, which is roughly here. It's in between the orbit of Mars and Jupiter, because notice Jupiter is out here. We have some other names for some groups of asteroids, but don't worry about those. I just want you to know that the asteroid belt is in between Mars and Jupiter. You might wonder where the other planets are. The answer is they're outside the orbit of Jupiter, but they're just not in the diagram. The diagram is zoomed in. Let's talk about the Kuiper Belt. This is a disk containing asteroids, basically small objects, icy rocky bodies, and it's defined as the region between 30 AU from the sun and 50 AU from the sun. And this is the Kuiper Belt. Pluto is actually part of the Kuiper Belt. It's a dwarf planet, and I'm going to show you its orbit in the context of the orbits of the context of the planets, as well as icy rocky bodies around the sun. And I think I'll be able to convince you that it really isn't a planet. There are at least around 70,000 objects in the Kuiper Belt with diameters greater than 100 kilometers. This is a slightly antiquated is not the correct word, but a slightly old figure. But the point is that there's a lot of objects in the Kuiper Belt that are very large. A 100-kilometer asteroid is a very large object. Let's say compared to the size of an object that would severely harm human life or other life if it were to hit Earth, for instance. Another thing you should know about the Kuiper Belt is that it is a repository of comets, particularly short-period comets. I'm going to get to the different kinds of comets in a little bit. We'll come back to this idea. But short-period comets are comets that have relatively short periods. The period is referring to the orbital period, which is the time it takes the object to orbit the sun. There are also long-period comets, but those generally live farther out from the sun. Right, we'll get back to that in just a bit. But first, as promised, I wanted to show you the Kuiper Belt. Here is another picture of the solar system. The sun and the terrestrial planets are in here. They're not even decipherable because they're so small here in this picture. And then the asteroid belt is here. So this is the orbit of Jupiter. Notice that we have the other 3 gaseous planets, Saturn, Uranus, and Neptune, here. They're actually unlabeled, but they're the blue circles. Those are the orbits of those planets. And then we have, I'll do this in red, then we have Pluto. Pluto is orbiting the sun along this trajectory. Now, I don't have trajectories of other asteroids here, with the exception of one or two. There's one here. But you can see that the orbit of Pluto doesn't look like the orbits of the planets, which are, again, in light blue. And in fact, if I show you an animation, it will be even more obvious. By the way, before we continue, this is the Kuiper Belt. This is the region that's outside the orbit of Neptune. I'm talking about, sorry, let me just go back to this, outside the orbit of Neptune from 30 to 50 AU, just to be clear about what I'm talking about. Now I'd like to show you an animation. You will notice that as I play this animation, all of the 8 planets orbit in the same plane. The solar system is like a pancake. It's very wide compared to its thickness. It's very thin. You will also notice that Pluto does not orbit in that plane. It orbits at an angle with respect to that plane. Let's do this again. Okay, so you can see here, I know the quality is not the best, but you can see that the 8 planets orbit in the same plane. If you look at the solar system on its edge, you can't even see the orbits now because they're all within that red area. But Pluto's orbit is at an angle with respect to that plane. And if I were to depict the orbits of asteroids and comets, they would look a lot more like Pluto's orbit, which is the one in white, rather than blue. They would look a lot more, sorry, I don't think I can make, I can. They would look a lot more like Pluto's orbit here, which is the one in white that I'm highlighting in red, than they would the planets. I hope that this has convinced you that if you hadn't learned that Pluto was a planet as a child, you wouldn't think it was a planet just looking at the orbits of the planets in the solar system, as well as knowing about asteroids. Let's move on now to the Oort cloud and comets. I did mention what a comet was, just very briefly. Let's see if we can define it a little bit more precisely. A comet is an icy and rocky object that passes close to the sun. In fact, it passes close enough to the sun where it sublimates. And sublimation is a fancy term meaning the ice turns into gas. If a comet is very far away from the sun, as they are most of the time, the ice will remain frozen because if you go, let's say, even to Jupiter, temperatures are extremely cold. That's because you'll be heated up by the sun if you're near Jupiter, but there's not nearly as much sunlight as there is, let's say, near Earth. As the comet gets close to the sun, the radiation that it absorbs becomes greater and greater, and this melts the ice. But the ice doesn't turn to water due to the chemical properties of the ice in space. It sublimates, which means it turns directly into a gas. This produces a nice tail that is oriented opposite the sun, because the comet, we're now trying to visualize here the comet going toward the sun, let's say, and then as the comet passes around the sun and comes back, then the tail will be pointed the other way. It's always pointed away from the radiation from the sun. I also want to point out that you don't get heat from the sun. This is one misconception that people have about astronomy and physics. When we say that the temperatures are cold around Jupiter, what we really mean is that if you, let's say you're in a spacesuit near Jupiter, you have to be in a spacesuit to live, your spacesuit is going to absorb radiation from the sun. Jupiter also emits radiation, but let's say you're not extremely close to Jupiter, you're just in that area, you're going to absorb radiation from the sun, and absorbing that radiation is going to heat you up. That's actually what we mean by temperature. You're going to have a temperature which is affected by the radiation from the sun. Now, actually, in this example, we're using a human. We have an innate temperature. Our bodies maintain homeostasis, so we keep a constant temperature around 37 degrees Celsius, I believe it is, in Celsius. But let's say we're talking about an inanimate object such as a rock, which has no intrinsic temperature. The temperature of the rock is just going to depend on the radiation it absorbs from the sun. So you don't get heat from the sun. It's not like being near a heat lamp. If you're near a heat lamp or a fire, you're getting heated up because the heat lamp is heating up the air around you, and that air is surrounding you, and then some of that energy will be absorbed by your body. That's a different process than how objects get heated in the solar system. You don't get heat from the sun because there's no air in between you and the sun. So you don't feel the sun's heat or temperature. You're only getting heated by the radiation that you absorb from the sun. Okay, I'm belaboring the point here, but I just want to make that clear, because when we think of objects getting heated, we actually think of not the process that occurs in space, but we actually think about what happens when you're close to a fire, for example. We think about getting heat from an object. But that only occurs because we have an atmosphere that can transfer thermal energy. Let's talk about an example of a comet, moving on. A famous comet, the most famous one, is Halley's Comet. There's millions of them, but in any case, Halley's Comet is very visible from Earth, and it passes by every 75 years. So the orbital period of Halley's Comet is 75 years. And this makes Halley's Comet a short period comet. A long period comet would have a period greater than 200 years. And one of the main repositories for long period comets, we believe, is something called the Oort cloud. And this is not really a cloud, quote unquote a cloud. It's not like clouds on Earth that they really just contain water vapor. By cloud, we just mean a very thin, wispy body that contains a lot of icy objects, and it exists far outside the orbit of Neptune. I would like you to watch a video on protecting Earth from near-Earth objects. This is actually a relatively long video, but it's interesting, and this may not be the most acute threat that we face as a species, but nonetheless, it's interesting to think about what would happen if we knew that an asteroid was coming toward Earth that was large enough to kill, let's say, all people. We would want to know about mitigation strategies. So I'm going to post this video on Blackboard, and I'd like you to watch it. Let's move on to a discussion of near-Earth objects in somewhat more detail. I mentioned to you that near-Earth objects are asteroids and comets that regularly approach Earth, and they approach Earth at a close distance. It doesn't mean, by the way, that they hit Earth. The vast majority of NEOs aren't likely to hit Earth. They don't hit Earth every year, obviously, then they would be destroyed, but they aren't necessarily likely to hit Earth. They just come within a certain close distance. There's a center for NEOs at NASA, and the goal of the center is to search and categorize NEOs so that we can determine any threats that are out there, any asteroids that might hit Earth in the future. This is one particular NEO here, this picture. This is an asteroid that was about 3 to 4 million kilometers from Earth when these pictures were taken. I want to talk a little bit about a quasi-morbid topic here, which is the threat of asteroid impacts. I'm talking about this in part because it's a serious topic, but also because I just want to discuss with you some research that's been done and use this as an opportunity to talk about how we speculate in science a little bit. So this stuff is pretty speculative, but we can look back into the history of life on Earth, and we can collect data about asteroid impacts and also extinction events. And we know from the data that extinction level asteroid impacts occur around every 100 million years or so, but this is statistical, so it's not that the clock is ticking and at exactly 100 million years from the previous incident we will have another incident. This is probabilistic, so it could occur anytime, but on average it occurs every 100 million years or so. By the way, I have a small typo, I'm sorry. I just noticed this should be million years. Sorry, I don't know how I missed that. But in any case, there are Other more short-term risks that we could discuss. Somehow I can't change this S. Sorry. Okay, it's just bothering me. All right, I will change it before I upload the PDF. But in any case, there are impacts that can cause local devastation. Asteroid impacts capable of devastating entire continents impact every 10,000 to 100,000 years or so. By devastating entire continents, I'm talking about in terms of the life forms. I'm not talking about destroying an entire continent. But if you live on this continent, your life will be pretty poor for a while. And asteroids capable of destroying whole cities, if they were to hit those cities, impact every few hundred years or so. An example of this kind of impact is the Tunguska event of 1908, which occurred over rural Siberia. Now, I should say that this sounds worse than it is because I'm saying that asteroids that could destroy cities impact every few hundred years. So that might sound as though a major city is going to be destroyed every few hundred years, which isn't true. These are simply asteroids that are capable of destroying cities if they hit cities. The vast majority of the Earth is not inhabited by cities, by people forming cities. Most of the Earth is pretty rural. Actually, most of it is water. So an asteroid that's capable of destroying a city that hits rural Siberia or the ocean is not going to destroy a whole city. It's just to be clear what I mean. An example of that is the Tunguska event, which was a very powerful event. I'm sorry I don't have a picture of it, but actually the pictures are very poor because this is an extremely rural area of Siberia. And basically, I don't remember the numbers, but some relatively large area, forested area, was destroyed. The trees were blown down by an asteroid. Here is some research that was done in the early 90s regarding asteroid impacts and the dangers of them and the relative likelihood. This paper down here, which is published in 1994, so it might be somewhat outdated, estimated the number of deaths that would occur on average from different impacts. I do want to say that there are asteroid impacts all the time, every single day, but the vast majority of them are completely harmless because we have an atmosphere. And so if the asteroid or comet or impactor, as they call it, has a diameter less than about 50 meters, then the estimated average number of deaths is going to be 0. It's going to really break up in the atmosphere. And these occur all the time. The Tunguska-like events, on average, they claim will produce a number of deaths equal to 5,000, but this is on average. So the vast majority of them either we wouldn't know about or will produce 0 deaths. And these occur every couple hundred years or so. And then we have the large, what they call subglobal events. These occur roughly every 30,000 years or so. These are the continent-wide, that's what they mean by subglobal. And on average, these, they claim, would kill hundreds of thousands or upwards of 1 million people. And then we have a global event. This would be an asteroid around 1 kilometer up to a few kilometers, something like that. These are pretty rare. These don't occur except every roughly 1 million years or so, maybe a bit less. But this would be truly catastrophic. And then the KT scale event refers to the extinction of the dinosaurs. This would occur if the asteroid had around a 10-kilometer diameter. These are quite rare. These are the extinction events I talked about earlier. Every 100 million years or so they happen. But this would be very catastrophic. Let's talk about some of the mitigation strategies. In other words, how do we deal with an asteroid that is impacting Earth in the future? Suppose we know that there's a 10-kilometer asteroid on our way. It will be here in maybe 10 years. We'll be lucky if we have 10, 20 years to prepare. How could we prevent it from hitting Earth? Well, there's a couple different strategies that people have talked about. You could blow it up with a nuclear weapon. You could deflect it with some kind of impact, a kinetic impact, meaning you can crash something on it. Or you could attach something to it that has a rocket, or you could try a gravitational tug. You can also try vaporizing it, with a laser. These are actually serious proposals that people have talked about. I would like you to watch this video on asteroid impact and deflection that I'm going to post to Blackboard. As I said, I'm not claiming that this is the most acute threat that humans face. I don't think that's true. But nonetheless, it's interesting to consider what we might do in the case of an asteroid impact. And this also gets you familiar with some of the more speculative aspects of science. I want to say one more thing, which is that finding asteroids is not so easy. Asteroids usually are pretty small. Even a 10-kilometer asteroid, which is big enough to do tremendous damage to human life, is quite small compared to, let's say, Jupiter, Uranus, Saturn, etc. 10 kilometers is a tiny distance compared to the size of the solar system. And asteroids don't emit very much light. They're very dark, and they're not easy to find, basically. If we want to find a planet, you would look for light that the planet reflects or emits. But asteroids don't emit or reflect very much light. And so it's not necessarily the case that we know all of the dangerous asteroids that are in the solar system. This is one of the challenges. There was a really nice video that I watched one time explaining the most recent findings about this and the estimates for the number of dangerous asteroids in each category that we haven't discovered yet, but that's a bit beyond the scope of the course. So anyway, thank you for watching this video. This finishes up our discussion of the solar system, lecture 9, and I will talk to you in another video.